Hi, welcome to the Signal Pad. Today I have another repair that I'm going to try. This is an HP 4338B, and this is a milliohmmeter. There's actually a reciprocal of this instrument, a 4339B. That's the high resistance measurement, and together they cover an enormous range of resistances, and essentially they place the dynamic range of measurement differently along the wide range of resistances people are interested to measure. Now this milliohmmeter can measure as little as 10 micro-ohm and as high as 100 kilo-ohm, which itself is really quite wide. And you may ask, well, what's so special about a milliohmmeter? Why can't you just use, a 7.5 digit meter you have or an 8.5 digit meter you have to measure that? Well, in theory you can, but there are differences. First of all, this measures the resistance at 1 kilohertz. And the other thing this does is that you can control very precisely how much current this puts into your device under test. And it can be as small as 10 microamp all the way to 10 milliamp or even maybe down to 1 microamp. This means that you can measure these tiny resistances with very little current. You can always measure a tiny resistance by putting a lot of current through it if you don't have enough dynamic range from your measurement unit. But this, of course, allows you to do it with very little current and measure it at 1 kilohertz. So I'll go over the principle of operation of this. It's similar to an LCR meter in a way, looking at the angles and taking a real part of the current voltage relationship. So it should be pretty cool to see what's inside it and if we can fix that. So let's go and turn it on. It does turn on. It takes its sweet time actually. It takes a while for it to boot. And there it is. 1997 is the date that it was there. Yeah, 1997. I think I was choosing where to go to university at that time. So there it is, ADC failure. I think you saw that error pass by. And I thought to myself, well, I know what the word ADC means, and I know what the word failure means. It should be very easy to fix, since we know both of those words. So let's go and open it up and see what's inside of it. And here's a look inside the unit. It's beautiful. This is a Japanese-made instrument. Like some of the other LCR meters I've been fixing, a lot of these form factors are actually from the same factory. So it's going to expect to be very, very good. So let's take a look and see what we have here. Main line coming in, voltage selection, protection, common mode, choke there, fuse, and the connection to the transformer are all on this board. The main transformer then goes into here with the bridge rectifier. And this unit over here is a DC-DC converter. Interesting, they've kept it separately in a cage, perhaps for isolation, or maybe they just had this as a module available. So the voltage that's after it's rectified comes back into here, and this gives you a whole bunch of other range of voltages, which then go into the digital board and analog board, and so on. At the input side over here, we have the main lines coming in from the high and low from the BNCs from the front. Now these wires, you can see they have ferrite cores around them. Now remember, these are coax, so there's ground on the outside. So you're not putting inductance on the main conductor, the main signal conductor, you're putting it on the ground essentially. And this allows you to take some of the transient effects off from the ground and further filter it, of course. Now here underneath this cage, we'll take a look at it probably. This is going to have our low noise amplifier front end. This is what is going to amplify the really, really small voltages or the currents that are required in order to capture exactly what resistance you are measuring. So it's going to have a part that's most likely long obsolete, but nonetheless, hopefully it still works. And once you amplify this, then you're going to have a very large signal, so then your SNR is not an issue after that. So this is a critical part for a noise issue from the front end. Relays may have perhaps to switch some range, and the rest of the circuits underneath this other board, and we'll have to take a look at that. Now this main board is clearly the digital board. We have LCD and keyboard and backlight connections up here, a couple of ICs interfacing, for the LCD driver and so on. Main firmware in a UV erasable part over there. You can see version U11 1997, which is what it said when it booted up. I wonder if I can get a new version of this, then we can upgrade the firmware as well. This is an EEPROM. This is to store perhaps calibration and store data or memory or key functions and so on. And it looks like that it is, there's a backup battery here, or I should say it's a supercapacitor. It's a 0.22 farad 5.5 volt supercapacitor, so they don't seem to have a battery in here that I can see at least. It looks like they're retaining that data with this. So if you unplug it for a while and you don't turn it off, perhaps you would lose it. And I don't recognize this part directly, but this is a Motorola 68000 processor, classic. You can find it in so many devices and some other interface ICs, and really nothing unusual, perhaps some more memory here. So might be DSP functions and computation to calculate the angles and figure out exactly what is going on and what the resistance is. So maybe that's what this unit is doing. Other than that, nothing really we can see on this side. I don't see an ADC here, and I wouldn't expect the ADC on this anyway, because the only way that this board can interface with the board underneath is with this cable, and you wouldn't want to send the ADC data through this anyway, because it's not going to be very good for noise and immunity and isolation. This is a GPIB connector, so some of these ICs here must be a GPIB controller. There is another handler interface you can see connected at the back. Remember, these are very fast instruments, so they can be used in manufacturing cycles to quick measurements. So you have some interface to connect it to a different device, perhaps a different test jig, or synchronize with some other test that you're doing at high speed in a manufacturing process. So looks really good. Now I don't see an ADC, which means that we're going to have to take this a step further. I actually stopped taking it apart. I was going to take this up, but I said, let's talk about this first. That's why these two screws are missing. I took them off. So let's go ahead and take this one off as well and see what's underneath it. And here's what's inside the unit underneath the main digital board. There's not that many components, a lot of interface ICs. Here's the main ribbon that connects to the digital side there. I recognize some CPLDs. There is a crystal over here. I believe it's running at 20 megahertz. There's a full oscillator running at 20 megahertz. Some transistors or regulators over here. I don't recognize this part, but this is an analog devices DAC. And this part I don't quite recognize, but I think that's probably the ADC just simply by what's surrounding it. So this is the component it's complaining about. Now, there are many things that could be wrong that it is complaining about the ADC. I'm not sure what that means. Now, this is an Asahi Kaise part, and it is very difficult to find. In fact, there is no schematic for this. No matter how much I searched, I couldn't find a schematic of this. There's a service manual, but it doesn't really tell you very much about what the components are and where the components are, so we have to figure that out ourselves. But it is worthwhile to looking at the block diagram of this instrument so we can get an idea of the signal flow there. And then find out why it says ADC failure. Now, this could be several things. Maybe the ADC is getting a very large signal and it doesn't recognize that. It doesn't calibrate on startup, so maybe that's the problem. Or maybe the ADC is dead. We have to investigate and find out what is going on and why it complains about it. So let's go and take a look and see what materials I can find on this. Discuss a little bit about the instrument's architecture, and then probably do some testing on it. It should be interesting to see what we can do. And because we don't have the schematic of this unit, we're going to have to do some investigation and some reverse engineering to figure out how it works in the hope that we can fix it. So first thing is to understand the principle of operation. Now, just like LCR meters, this type of resistance meter is going to use a vector measurement and is going to measure the angle between the current and the voltage across the device under test. And it's going to take the real part of that, which would be the resistive part of it, and then it's going to give you that as the measured resistance. Now, this unit is special because it limits the voltage across the device under test to below 20 millivolts. So it's a tiny, tiny voltage across the device that you're trying to measure, but yet it can measure down to 10 micro-ohm, which is very, very high sensitivity. So it's got a very high sensitivity, very low noise front end in order to be able to accomplish this, and appropriate amplifications and so on. So if you look at this, we got an ADC at the end, and this seems to be the part that is failing, or at least communication is failing with the ADC. And there are some filterings and attenuation required to condition the signal so that the ADC can sample it, and it's going to put the signal within the full scale of the ADC. Of course, you can't just put 20 millivolts into an ADC. You'll get nothing out. So having said that, there's a switch here. That switch is going to either measure from sense amplifier up here, or it's going to measure across the voltage sense amplifier. So there's a current and voltage measurement that we would expect to get in order to calculate the vector and calculate the resistance part of it. And as you can also imagine, this is an AC measurement done at 1 kilohertz, not at DC. So it has its own advantages when you do this measurement at a kilohertz. So now that we know kind of how it works, and we can have our eye out on these components, we can find the ADC, we can find various components over here, but really we're dealing with the ADC's connection to the main CPU. So it goes through various latches and timers and flip-flops and so on, which I will talk about, in order to communicate with the main processor, which is on the separate board. So what about the ADC itself? Well, it turns out that there's almost no information available about this ADC. I had a really hard time finding anything at all about it. In fact, the only thing I found was this other ADC, and this other ADC is the AK9202, which is down here. I don't know if you can see my cursor. This model, this is not even the model that's on this board. The one that's on this board is an AK9201, so it's fairly similar. They use the same architecture. They're both a successive approximation ADC. I've done tutorials on DACs and ADCs, Nyquist, as well as Delta Sigma. I haven't done a a tutorial on a successive approximation one, but the principle is fairly simple. It's actually a DAC inside, and that DAC is going to run across a series of voltages, and that voltage is going to get compared with some other value, and then that's how you know you've reached your analog value. So it basically has a counter inside, or the most simple form of a successive approximation ADC would be just counting up and then using a DAC and then comparing with the input voltage and so on. And you can see there are reference buffers and reference voltages that come in. These particular ADCs have 2 channels, and I think that this instrument only uses one of the channels, but there's a channel selection. Obviously has separate analog and digital grounds as to be expected, has positive and negative power supplies. It's a fairly old part, so it requires negative supply for the DAC. It has a built-in microcontroller, and this is interesting, and calibration SRAM and all this, and there's a whole lot of control signals, including this clock and some of these things that are required to communicate and talk with this ADC, as well as an external crystal that is required to run the microcontroller and the state machines inside this A to D converter. So that's all the information we have about it, and it's actually not very helpful, and I'll tell you why. Because I found out that this ADC is used in a lot of the Roland, I don't know exactly how you pronounce it, instruments for music generation and music synthesis and MIDI controllers and all the stuff that Roland makes, and the schematic for that is available. So that's pretty interesting, because it tells us how this ADC is used in a different system, different from this instrument. But as you will see, this actually caused quite a bit of confusion because it's used a little bit differently here. So first thing to note is that there's a lot of these control signals which they have just simply left alone and they're not using. They're generating their reference voltage using an op-amp in forward following mode with some resistive dividers, give you a clean reference voltage. This is probably not very critical for this Roland synthesizer, so they're only using a resistive divider. It's not really that important. Some filtering at the input and output, so that makes sense. So you're generating some relative value for the DAC basically as a reference. The analog and digital voltage are just fed using some simple low-pass filtering, and at the bottom here similarly coming from a negative power supply. Again, very straightforward. For the Roland music synthesizer here, they have a left and the right channel coming from some op-amps and doing some sampling and so on. So that is also pretty straightforward, and we're only using one of these 2 channels on this device instrument, so that's also pretty straightforward. Clock here is coming from a 25 megahertz source. The source here on this instrument is 2048, so 2.048 megahertz, and you can imagine why they're using 2.048, because it's a nice divisible 2 to the power of n number, so they must be using that for some purposes. Now if you look, there's a code that's grounded here, and then there is the clock, data, and the left and the right channel. Now the left and the right channel is not that important because we're only using one of the channels in this instrument, so we can ignore that one. Digital ground is pretty straightforward, and then the reset, obviously you have to bring the device out of reset, and then there's a hold signal here. So if you look at the way this works, if you're familiar with, let's say, serial interfaces, I2C interfaces, you have to have a slave and a master. Now by the fact that there is an inverter here, that tells us that this device, this ADC in this design is being used as a slave, meaning that it's never in control of the timing of the processor. The processor is in control of the timing of the ADC. That's why there's an inverter here, meaning the signal flowing is into the clock. Now that was the confusion, because in this circuit, in this instrument, this is not how it works. In fact, there is no inverter, and I traced this as well as I could, and it looks like it goes only to inputs, which means that in this device is going the other way, which also points to the fact that this ADC is capable of acting as the master on the serial bus. And that took a while to figure out, because I was convinced that I was reading the PCB wrong. But indeed, now when you think about it, it kind of makes sense, because it has its own crystal and so on, which means that you can tell the ADC when to do conversion using this hold signal, but at the same time, the ADC is going to clock out the data using its own clock. And if you look here, there is another pin, this pin 27. This pin 27 is called SCK mod, which I think is the SCK mode, essentially. It means that whether you want this device to act as the master or the slave. So they have left this alone, but on this design, they've pulled it down, which means that that's probably the other state. These must all have pull-ups and pull-downs internally. So it all kind of comes together. It makes sense of how this is supposed to work in this system. Now things are pretty complicated on this board, and we're going to go back to the board and I'm going to talk about it. And what we can do is we can take this ADC out of the board, put it on a PCB, and measure it on its own and see if it generates clock and generates data by itself. If it does that, then the ADC is probably working. And then we can check to see if it does the same thing when it is inside the instrument or not, and if it's still generating clock and data. If it isn't, then there's something, some timing, some signal is missing from the board itself that's basically not getting the ADC started. So there's a lot that I said and there's a lot that I investigated, but I think we should be able to take this one step at a time, go to the board and then check the breadboard that I put together with this ADC, so we can do these measurements one step at a time and see if we can get some results. So here I have taken the ADC out of the unit and put it on a breadboard. It's a pretty desperate attempt to try and figure out how it works. And I actually happen to have exactly the same crystal to run the clock into the unit there. This is a 20.048 megahertz clock, and I think I may have accidentally said 2 megahertz before, but it's actually 20 megahertz, and that goes directly to the clock input. I also have a bunch of switches here and pull-up resistors there that allows me to pull various nodes high and low, for example, like reset and mode and latch and so on, to see what happens to the ADC and whether I can make it behave like a master unit and take control of the bus and the clock be generated directly from this unit as opposed to coming into it. And that proves that if we can do this, that indeed this ADC is able to define the timing of the data that it comes out as opposed to being the slave in that mode. So I'm looking at a couple of things here. Sorry for the probes that are in the way. I'm looking at the clock and the data coming out of it, so that we can look at it under the oscilloscope. And of course, I'm going to use the MSO5 series. It has 8 analog channels, which is great. Now you may ask, why don't you just use a logic analyzer? Well, for debugging, an analog channel is much more useful because you can catch unusual tri-states or weak pull-ups or weak pull-downs much easier when you have an analog channel. So we're going to take advantage of that when we're debugging the unit as well. So here it is. Let's go now to the screen of the oscilloscope and take a look and see what happens as I play with various inputs of this ADC, whether we can make it to generate the clock. And here we have the screen of the MSO5 series from Tektronix, and I have all the 8 channels enabled here, and something really satisfying about having 8 analog channels like that. So I have labeled them, then crystal, standby, hold, clock, sleep, reset, SCK mode, and data, which are the various pins that are on the ADC. So now we can go ahead and turn it on, apply power to it, and see if we can get it to generate anything from the clock. And if it does, then we confirm that it can actually act like a master on the bus, and that we can also figure out what configuration of these signals are required to get it to start. So let's first thing first is to apply power. So here's power, and as soon as I apply power, the crystal starts. Now the crystal is obviously going to look completely filled, and the reason is because I'm looking at it from very, very far away, and I'm triggering on a different channel. No, I'm triggering on this channel, but I'm triggering on both of the rising and falling edge. There it is, so you can see the clock is indeed there. So let's go all the way back out again. So let's see what is going on right now. So hold is low, and the data is sitting high. CH mod or SCK mod is sitting high as well, and the clock is sitting low. So let's try and see what happens if I change CH mod. I'm going to flip it from a high to a low, and check it out. As soon as I do that, SCK begins to operate, and you can see it's putting out bursts of data. And let me change the trigger to channel 4. There we go. You can see that now we have 16 bits that are coming and going. There's a little space in between them where there's a delay, where there's no clock. It's just bytes of 16 bits coming out of the unit there. So, and the data is toggling. There's no analog signal at the bottom, so this is whatever it is, the lowest value is being measured, probably just measuring 0. So it does indeed work when CH mod is low. And that's also when hold is low. Let me see what happens when I pull hold high. If I do that, so if I pull hold high, there is also no activity. So 2 things are required. Obviously, reset needs to be, this reset is not connected, by the way, that's why it's sitting low, but it should be high. It's an active low signal. So reset should not be there, hold should be low, and CH mod should be low. And under those conditions, we can put it in those conditions again, pulling CH mod low, there it is. So CH mod low, hold low, clock will operate. And look, it's now generating some other data. Interesting, must be picking up some parasitic signals there. So it works. Therefore, now I can go back to the unit itself, put the ADC back, and monitor the same signals on the unit and turn it on and see if it has any kind of activity that resembles this. And if it doesn't, then something else is wrong. The problem is definitely not with the ADC. Something else is causing the communication with the ADC to break down. Now that I know that this can act as the master, it also makes sense how the system is architected. We're going to take a look at the PCB. Now things are coming together a lot better. So let's go back to the board, take a look at it, and see what we can find out. All right, so here's the ADC back in the unit on a socket for easy removal. And now we can investigate a little bit better what's going on. So here's the crystal for the ADC, which is what I was basically using. Now, because this is a master here, and they don't want to use a microprocessor here, they have to basically build all the logic required to time everything on this analog board and communicate with the main CPU on the different board. So there's a lot of little things that I have to put in, a lot of glue logic, a lot of components. Now, everything over here, latches, inverters, buffers, tri-state buffers, all these can be replaced, and we can find replacement for them, except for two components, this component and this component. Now, these two components are PAL devices. They're essentially programmable array logic devices, CPLD type devices. But the problem is that these have unique serial numbers written on them, part numbers, and these look like to be HP Agilent part numbers, meaning that they have a specific program in them. And I'm afraid that these are mask ROM programs. So they're programmed at the time of fabrication by defining the mask of the semiconductor itself. And this is a common technique if you're wanting to use the same program or the same configuration on many chips, and you don't have to program them if you don't intend to update them, for example. You can just permanently build them with that code into it. And people have done amazing things at reverse engineering these things. So unfortunately, if this and this are dead, then we're in trouble, because these are very difficult to replace. Now, this component, I have no idea what it is, but it doesn't seem to be interacting with the ADC very much, at least for the time being. I can't see any connection. There's a DAC over here and some voltage, reference voltage generation over here. And this component here is a timer. It's essentially an interrupt generator. And when you don't have a processor and you want something that has timekeeping, that tells you how many clock cycles have passed, you can use a timekeeper like this one. This has 3 timers built into it. So this is kind of building a poor man's processor, essentially. And it's a very complex state machine. So that these two kind of work together in order to communicate with the timer and with the ADC. The signals that control the ADC, such as the hold signal that we just measured, is actually coming from this component itself. The CH mode is permanently tied low, which makes sense on this, which is what it should be. So CH mode is something we don't have to worry about. But hold is coming from this one. And the data going out of this going to a couple of latches and flip-flops and shift registers, which makes sense. They shift the data in because it's coming out serial, and then they latch it out parallel into the processor. So all of that works nicely. The question is, what is broken on here? Is it this components, which would be pretty bad? Now, I have a desperate way of attempting to fix this. I happen to have an LCR meter, an older version of the one that you've seen on my bench, the A model. These are B model instruments. And they used exactly the same 2 parts because they haven't really changed this part of the board between the A to B model. So in a desperate attempt, I could take that component from that other one, replace it with this, just to make sure that this is not the problem. And that would be, you know, if we can remove that as a doubt, then we can investigate other things much easier. But if this is broken, yeah, I don't know what else we can do, because I don't want to break another instrument to fix this one. That kind of defeats the purpose, even though an LCR meter, I already have a better one in my lab. The other thing I can do is see if I can copy the content out. If they have not put the bit protection that prevents you from reading these PAL devices in the mask ROM, then I can copy it out and then burn it into an electronically erasable version of the same chip, put it back in there, and then we have a duplicate. So I'm going to attempt that by removing it from the other board and see if I can basically do the same thing. It's interesting to see that the other board is very similar to this one, only the front end on the left here is different. So everything here is kind of sitting on the table. Let me show you if I can get the camera to move. There it is. You can see the screen over there. I've got my isolation transformer. It's yet another advantage of having the isolation transformer, because I don't have the main transformer of this unit on the bench here, and I'm just simply generating a 17-volt AC signal, which is what is required to go into the rectifier of this unit. So that's another advantage of having an isolation transformer. You can just step the voltage down and don't have to worry about dealing with live wires there. So it all looks great. I'm going to go ahead and remove that other PAL device from the other board, see if we can extract the program from it, and see what we can do with that. So it may seem like I'm jumping the gun, going and trying and replacing component before doing any measurement. I actually forgot to record that part. So I did do the measurement. I did exactly what I said I would do before. I connected signals to the clock, the hold, the standby, the reset, everything. I monitored the hold and all the other pins in here. And indeed, the hold pin never goes low. So this unit does not generate the clock at all because this component here never tells the ADC to begin sending out data. So something is missing in these connections in between these components, and there is so many of them here, so you don't know which one is the cause. That's why I want to start from the one that I basically have no control over so that we can eliminate that from the equation. But yes, I did do the measurement. I took a look at it. I turned it on. The hold never changes. No clock comes out. No data comes out. Crystal is working. Reset is working. CHmod is working, everything else is fine, but the hold is not being generated, which is this is a unit responsible. That's why I wanted to do that step. So now that you know, let's go and take it out of the unit. And here you can see I've changed the IC. I took it from the old LCR meter. Like I said, it's A version, so it's not as valuable as this unit. But nonetheless, now that one obviously is not going to work. But here's the one I took out of this unit. So if the unit still has a problem, that means this is not the issue. We can put this one back, so I'm still saving it. I haven't copied the code from this. I actually tried. I couldn't get anything out of it, unfortunately. Either the protection bit is enabled or something is wrong with my programmer. So now that it's all back together, let's go ahead and turn it on and see if that error has cleared. And if it is, that will be a huge step forward. Then we can put it back together and see if it's still working. Okay, here's the moment of truth. Let's turn it on. So let's see. And do remember that it did take a bit of time before things came back. There you go. 1997. That's still normal. And do we get the error? And check it out. That is nice. So not too bad for replacing only one component for something without a block diagram or schematic or anything. So this is definitely the problem now. Now I'm seeing minus 36 kilo ohm, but this is not sitting connected in its case because one of the inputs should be grounded. So it's not properly connected. So let's go and figure it out and put it back together in the case and see if it comes back to some kind of a reasonable value, or perhaps it has another problem which we have to diagnose. But definitely minus 36 kilo ohm could mean anything when it's not calibrated. So here are the BNC inputs at the input of the instrument, and I just wanted to show you this before I put it back together. So you can see the three of them go to the device under test. One of them is directly referenced to ground. Now because these BNCs have floating grounds, they actually have back-to-back protection diodes to the ground itself, along with some capacitors there, so that to prevent these voltages to ever exceeding the forward bias voltage of these diodes. So it's interesting to see the effort going through to do this at the top. These ICs are the LCD controller. So now we can go ahead and put this one back as well and connect it to the inputs of the front-end amplifier. Okay, everything's back together. I actually noticed that these plastic standoffs which hold the ferrites against this so that they're not just flapping all over the place inside the unit were missing from this instrument, meaning that somebody had actually gone in here and done some work and taken these out, maybe because they wanted it for a different unit. So this was definitely something where some repair attempt had been made. So I'm glad that was the only thing that was missing. There was also some screws from the other side that were also not there. So now that it's all back together, I'll just put the cover on it. And here's the unit up and running, and it seems to be nicely functional. So right now I have this fixture connected to it. This is the HP16047D. It's the wrong fixture for this instrument. It's not the one you're supposed to be using, so I can't get very reliable measurement out of it. This is really for an LCR meter, but of course it still can do some measurements on it. Test fixtures intended for this instrument are, for whatever reason, really expensive. So I'm going to have to see what I can find on eBay if I can find a proper one, but we can do a measurement just to see if it's working. So here I have a piece of copper that I've put in between the two terminals as my 0 ohm reference, so we can zero the instrument with that. My Kelvin clips that I plug into here that you've seen me use with the LCR meters, unfortunately doesn't work with this. The reason is because when I try to zero that, there's too much series resistance in the Kelvin clips, and it's out of the range for the zero functionality for this. So let's go and zero this one. We can do a short measurement. There it is. It's going to correct that, and it's going to give us roughly about 0. Now remember, this number here is in milliohms, so it's absolutely tiny, and it's going to give us here the reactive part as well, also in milliohms, and you can set it to be angles and so on. So it actually can measure capacitance if you really wanted to measure some values of capacitance as well. So having said that, now we can remove that and try and measure a resistor that I have. Now I'm doing 8 averaging here, as well as the fact that I've left the level on auto, but you can choose the level to be anything between 1 micro to 10 milliamps in terms of the current that it puts through the DUT. So we're going to stick with auto here, which is fine for our purposes. So having said that, let me zero this one more time. This is really not a very good setup for making very small measurements, but there it is. So let's go and remove this now. I'm going to put my resistor in its place. It just barely fits in here. So let's see if I can get that to go back into where it was. There we go. And you can see when I rotate this, I'm going to get slightly different values because the connection is just simply not very good. But this is a 1 ohm resistor, 1%. So we're reading, fairly close if you get it to make good contact. But of course, you don't want rotating the device to change your measurement. But it does demonstrate that indeed this thing works, and it works quite well. And I'm very happy that we managed to get it up and running. But of course, I don't have a replacement component yet. So let me show you that component that I'm looking for. Maybe one of you guys have one that you can send me. And here's the component in question, the PAL device that I had to remove from the old LCR meter, and you can see it has a serial number on it, and this is the code that you would need in order to replace it with the correct part. As you can see, the part number for the device itself is not really relevant because you can get blank devices. It's the serial number that really matters. So having said that, if you have one of those, I can purchase it from you. If you want to send it to SignalPath so we can get the other unit back up and running, that would also be fantastic. Now, as always, thank you so much to my Patreon supporters. All these instruments that you see are purchased because of your support. These things are not cheap even when they're broken. So thank you again. And as always, if you subscribe, like, or comment on the video, it increases the engagement of the video, so it will reach a wider audience. That's really the only reason why that matters. So having said that, I hope you enjoyed this episode. I'll see you next time.